faults in the insulation or wiring of the controller can create a path for current to flow to ground. Switching transients or other high-frequency noise from the controller can couple onto the power lines and cause interference. If the controller is wired close to other power lines or equipment with heavy current draw, inductive coupling can induce current into the controller's ground wire. A faulty neutral ground bond in the junction box or elsewhere in the system can allow current to flow from the neutral wire to ground. If an isolation transformer is used to isolate the machines from each other, a fault in the transformer can allow current to leak to ground. If the junction box is not properly grounded, current can flow through the equipment grounding conductor and to ground. Loose connections in the junction box or at the machines can create intermittent ground paths. The troubleshooting steps are as follows. Firstly, isolate the machine. Disconnect the machine with the controller that is causing the ground current and see if the problem goes away. Secondly, check the machine controller. Inspect the controller for any visible damage or loose connections. Use a megometer to test the insulation resistance between the controller terminals and ground. Thirdly, check the junction box. Ensure that the neutral ground bond is properly connected and secure. Tighten all connections in the junction box. Fourthly, check the isolation transformer. If an isolation transformer is used, measure the voltage between the primary and secondary windings to ensure that it is operating properly. Fifthly, check the grounding system. Verify that the equipment grounding conductor is properly connected at all points, including the junction box, machines, and transformer. When troubleshooting ground current issues in machines, several potential causes should be investigated methodically. Firstly, a ground fault within the machine's controller is a prime suspect. This occurs when there is a failure in the insulation or wiring of the controller, creating an unintended pathway for current to flow to ground. Such faults can arise from damaged wires, degraded insulation, or component failures within the controller itself. Secondly, high-frequency noise generated by the controller can contribute to ground current. Controllers, especially those employing switching power supplies or other high-speed circuitry, can produce switching transients and other forms of high-frequency noise. This noise can couple onto the power lines and induce currents in the grounding system, leading to measured ground current. Thirdly, induced current can be a factor, particularly if the controller's wiring runs in close proximity to other power lines or equipment with significant current draw. Inductive coupling between these conductors can induce current into the controller's ground wire, which then manifests as ground current. Fourthly, a faulty neutral ground bond can create a path for current to flow from the neutral wire to ground. In electrical systems, the neutral and ground conductors are typically bonded together at a single point, usually at the service entrance. If this bond is compromised or if additional bonds exist elsewhere in the system, current can flow through unintended paths, including the ground conductor. Fifthly, if an isolation transformer is used to isolate the machines, a defect within the transformer can cause current leakage to ground. Isolation transformers are designed to prevent direct current flow between the primary and secondary windings, but a fault in the transformer's insulation can create a path for current to leak to ground. Sixthly, an improperly grounded junction box can contribute to ground current. The junction box, which serves as a central connection point for the machine's electrical wiring, must be properly grounded to ensure that any fault current can safely return to the source. If the junction box is not adequately grounded, current can flow through the equipment grounding conductor into ground, resulting in measured ground current. Seventhly, loose connections within the junction box or at the machines themselves can create intermittent ground paths. Loose connections can increase resistance and create voltage drops, leading to current flow through alternative paths, including the grounding system. To effectively troubleshoot ground current issues, a systematic approach is essential. Firstly, isolate the machine by disconnecting it from the power supply. If the ground current disappears when the machine is disconnected, this indicates that the fault lies within the machine itself or its associated wiring. Secondly, inspect the machine controller for any visible signs of damage, such as burnt components, cracked insulation, or loose connections. Use a megometer, also known as an insulation resistance tester, to measure the insulation resistance between the controller terminals and ground. A low insulation resistance reading indicates a potential ground fault within the controller. Thirdly, carefully examine the junction box to ensure that the neutral ground bond is properly connected and secure. Verify that all connections within the junction box are tight and free from corrosion. Use a multimeter to measure the voltage between the neutral and ground conductors. A significant voltage reading indicates a potential problem with the neutral ground bond. Fourthly, if an isolation transformer is used, measure the voltage between the primary and secondary windings to ensure that it is operating properly. A high voltage reading indicates a potential fault within the transformer. Fifthly, verify that the equipment grounding conductor is properly connected at all points, including the junction box, machines, and transformer. Use an impedance tester to measure the impedance of the grounding conductor. A high impedance reading indicates a potential problem with the grounding system. When using a megometer to test insulation resistance, it is crucial to follow proper safety precautions. Firstly, disconnect the equipment from the power supply before testing. Secondly, discharge any stored energy in the equipment before connecting the megometer. Thirdly, use the appropriate voltage range for the equipment being tested. Fourthly, interpret the megometer readings correctly. A high insulation resistance reading indicates good insulation, while a low reading indicates poor insulation. Several factors can influence ground current measurements, including the type of equipment, the wiring configuration, and the environmental conditions. Firstly, different types of equipment have different leakage current characteristics. Some equipment, such as switching power supplies, may have higher leakage current than others. Secondly, the wiring configuration can affect ground current measurements. Long wire runs, parallel conductors, and improper grounding can all contribute to ground current. Thirdly, environmental conditions, such as humidity and temperature, can affect insulation resistance and ground current measurements. Ground current is the current that flows through the grounding conductor of an electrical system. Ideally, current should only flow through the intended circuit conductors, but in reality, some current can leak to ground due to insulation imperfections, capacitive coupling, or other factors. While a small amount of ground current is normal, excessive ground current can indicate a problem with the electrical system. Excessive ground current can pose several hazards. Firstly, it can create a shock hazard. If a person comes into contact with a grounded metal object while there is excessive ground current flowing, they could receive an electric shock. Secondly, it can cause equipment damage. Excessive ground current can overheat electrical components, leading to premature failure. Thirdly, it can interfere with the operation of sensitive electronic equipment. Ground current can create noise and interference that can disrupt the performance of computers, communication systems, and other electronic devices. To minimize ground current, it is important to ensure that the electrical system is properly designed, installed, and maintained. This includes using high-quality insulation, minimizing wire lengths, providing proper grounding, and regularly inspecting and testing the system. If excessive ground current is detected, it is important to identify and correct the cause as soon as possible. This may involve inspecting the wiring, testing the insulation, and repairing or replacing faulty components. Electrical codes and standards provide guidance on how to design, install, and maintain electrical systems to minimize ground current and ensure safety. These codes and standards are developed by organizations such as the National Fire Protection Association, NFPA, and the International Electrotechnical Commission, IEC. It is important to follow these codes and standards to ensure that the electrical system is safe and reliable. Grounding is a critical aspect of electrical safety. Grounding provides a low impedance path for fault current to flow back to the source, allowing overcurrent protective devices, such as circuit breakers or fuses, to quickly trip and energize the circuit. This helps to prevent electric shock and equipment damage. There are two main types of grounding systems: firstly, equipment grounding, and secondly, system grounding. Equipment grounding involves connecting the metal enclosures of electrical equipment to ground. This ensures that if a fault occurs within the equipment, the fault current will flow to ground, tripping the overcurrent protective device. System grounding involves connecting the neutral point of the electrical system to ground. This provides a reference point for the voltage and helps to stabilize the system. A neutral ground bond is a critical connection in the grounding system. It is the point where the neutral conductor is connected to the ground conductor. This bond ensures that fault current can flow back to the source through the grounding conductor. It is important to ensure that the neutral ground bond is properly installed and maintained. A faulty neutral ground bond can create a shock hazard and interfere with the operation of sensitive electronic equipment. Ground fault circuit interrupters, or GFCIs, are another important safety device. GFCIs are designed to detect small amounts of ground current and quickly interrupt the circuit. GFCIs are commonly used in areas where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor locations. Surge protection devices, or SPDs, are used to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, power grid switching, or other events. SPD divert the surge current to ground, preventing it from damaging the equipment. Electrical noise is unwanted electrical signals that can interfere with the operation of electronic equipment. Electrical noise can be caused by a variety of sources, including electromagnetic interference, ME, radio frequency interference, RFI, and ground loops. There are several techniques that can be used to reduce electrical noise, including shielding, filtering, and grounding. Shielding involves enclosing electrical equipment in a conductive enclosure to block electromagnetic radiation. Filtering involves using electronic circuits to remove unwanted frequencies from the electrical signal. Grounding involves providing a low impedance path for noise current to flow back to the source. Harmonics, a distortion of the electrical waveform. Harmonics can be caused by nonlinear loads such as electronic equipment, variable frequency drives, and arc furnaces. Harmonics can cause a variety of problems, including overheating of electrical equipment, increased energy consumption, and interference with the operation of sensitive electronic equipment. There are several techniques that can be used to reduce harmonics, including using harmonic filters, using phase-shifting transformers, and using active harmonic correction. Power quality refers to the characteristics of the electrical power supply. Good power quality is essential for the reliable operation of electronic equipment. Poor power quality can cause a variety of problems, including equipment malfunction, data loss, and premature equipment failure. There are several factors that can affect power quality, including voltage sags, voltage swells, harmonics, and transients. Power quality monitoring is the process of measuring and analyzing the characteristics of the electrical power supply. Power quality monitoring can help to identify and diagnose power quality problems. Power quality mitigation is the process of taking steps to improve power quality. There are several techniques that can be used to mitigate power quality problems, including using voltage regulators, using surge suppressors, and using harmonic filters. Electrical safety is a critical concern in any workplace. Electrical hazards can cause serious injuries or even death. It is important to follow proper electrical safety procedures to prevent accidents. Some common electrical safety procedures include using lockout-tagout procedures, wearing personal protective equipment, and inspecting electrical equipment regularly. Lockout-tagout procedures are used to prevent accidental energization of electrical equipment during maintenance or repair. Personal protective equipment, PPE, such as rubber gloves and safety glasses, can protect workers from electrical hazards. Regular inspection of electrical equipment can help to identify and correct potential problems before they cause an accident. Arc flash is a dangerous electrical phenomenon that can occur when there is a short circuit in the air. Arc flash can generate intense heat, light, and pressure, which can cause serious burns, blindness, and other injuries. Arc flash studies are used to determine the potential arc flash hazards in a workplace. Arc flash PPE, such as arc-rated clothing and face shields, can protect workers from arc flash hazards. Electrical training is essential for anyone who works with electrical equipment. Electrical training can help workers to understand electrical hazards and how to prevent accidents. There are several different types of electrical training available, including classroom training, on-the-job training, and online training. A qualified electrician can provide valuable assistance in troubleshooting and resolving ground current issues. An electrician has the knowledge, skills, and experience to safely and effectively diagnose and repair electrical problems. It is important to hire a qualified electrician who is licensed and insured. When hiring an electrician, be sure to ask for references and check their qualifications. Electrical inspections are an important part of maintaining a safe electrical system. Electrical inspections can help to identify potential problems before they cause an accident. Electrical inspection should be performed by a qualified electrician. Electrical codes and standards provide guidance on how to design, install, and maintain electrical systems. These codes and standards are developed by organizations such as the National Fire Protection Association (NFPA) and the International Electrotechnical Commission (IC). It is important to follow these codes and standards to ensure that the electrical system is safe and reliable. The National Electrical Code (NEC) is a widely adopted electrical code in the United States. The NEC provides requirements for the safe installation of electrical wiring and equipment. The NEC is updated every 3 years. The NEC covers a wide range of topics, including wiring methods, grounding, overcurrent protection, and equipment installation. Article 250.4 of the NEC covers grounding and bonding requirements. Article 300.11 of the NEC covers securing and supporting wiring methods. Article 310.15 of the NEC covers ampacity of conductors. Table 310.15. B16 in the NEC provides ampacity ratings for conductors. Article 408.3 of the NEC covers overcurrent protection. Article 430 of the NEC covers motors, motor circuits, and controllers. Article 500 of the NEC covers hazardous locations. Proper grounding and bonding techniques are essential for electrical safety. Grounding and bonding help to ensure that fault current can flow back to the source, tripping the overcurrent protective device. Grounding and bonding also help to reduce the risk of electric shock. Grounding electrodes are used to connect the electrical system to the earth. Common grounding electrodes include ground rods, ground plates, and metal water pipes. Bonding jumpers are used to connect different metal parts of the electrical system together. Bonding jumpers help to ensure that all metal parts are at the same potential, reducing the risk of electric shock. Overcurrent protection devices, such as circuit breakers and fuses, are used to protect electrical circuits from overloads and short circuits. Circuit breakers are resettable devices that trip when the current exceeds a certain level. Fuses are one-time devices that melt when the current exceeds a certain level. It is important to select the proper overcurrent protection device for the circuit. The overcurrent protection device should be sized to protect the conductors and equipment in the circuit. Short circuit current is the current that flows during a short circuit. Short circuit current can be very high, and it can cause significant damage to electrical equipment. It is important to protect electrical circuits from short circuit current. Arc fault circuit interrupters, or RFCs, are designed to detect arc faults and quickly interrupt the circuit. Arc faults are a type of electrical fault that can cause fires. RFCs are required in many areas of the home, such as bedrooms. Surge protection devices, or SPDs, are used to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, power grid switching, or other events. SPD divert the surge current to ground, preventing it from damaging the equipment. Electrical maintenance is essential for ensuring the safe and reliable operation of electrical equipment. Electrical maintenance should be performed on a regular basis. Electrical maintenance includes inspecting electrical equipment, tightening connections, and testing insulation resistance. Electrical testing is used to verify the integrity of electrical circuits and equipment. Common electrical tests include insulation resistance testing, continuity testing, and voltage testing. Insulation resistance testing is used to measure the resistance of the insulation on electrical conductors. Continuity testing is used to verify that there is a continuous path for current to flow. Voltage testing is used to measure the voltage in an electrical circuit. Power quality analysis is used to identify and diagnose power quality problems. Power quality analysis involves measuring and analyzing the characteristics of the electrical power supply. Power quality analysis can help to identify problems such as voltage sags, voltage swells, harmonics, and transients. Energy efficiency is the process of reducing energy consumption. Energy efficiency can save money and reduce greenhouse gas emissions. There are many ways to improve energy efficiency, such as using energy-efficient lighting, using energy-efficient appliances, and improving insulation. Renewable energy is energy that comes from sources that are naturally replenished, such as solar energy, wind energy, and hydropower. Renewable energy is a clean and sustainable source of energy. Solar energy is energy that comes from the sun. Solar energy can be used to generate electricity or heat water. Wind energy is energy that comes from the wind. Wind energy can be used to generate electricity. Hydropower is energy that comes from the flow of water. Hydropower can be used to generate electricity. Sustainable energy is energy that meets the needs of the present without compromising the ability of future generations to meet their own needs. Sustainable energy is energy that is both environmentally friendly and economically viable. The controller's interaction with other devices can also contribute to ground current issues. Firstly, the controller's power supply should be checked for proper grounding and isolation. Secondly, signal cables connecting the controller to other devices should be shielded and properly grounded. Thirdly, any external devices connected to the controller, such as sensors or actuators, should be inspected for ground faults. Finally, the machine's power distribution system should be checked for proper grounding and bonding. This includes verifying the integrity of the equipment grounding conductor, the neutral ground bond, and the grounding electrodes.